All right, welcome. In this video, I'm going to continue talking about minimum spanning trees, and I'm going to look at specifically Kruskal's algorithm. In my last video, I introduced the idea of minimum spanning trees, and I discussed Prim's algorithm. If you've skipped that video, you might want to take a quick trip back there and just take a look at minimum spanning trees and the definition before jumping into this video, because I'm going to start right with the problem and the algorithm. So again, maybe just a quick review of the problem. We've got a weighted, connected, undirected graph, and our goal is to find the spanning tree, the tree that spans the original vertex set, but potentially with different edges, a subset of the edges, in part, to be specific. But the one that has the minimum total weight. So the spanning tree with minimum total weight. And in the last video, we looked at Prim's algorithm to do this. And independently and somewhat around the same time, Kruskal developed this other algorithm, actually two algorithms with very similar features. Following an insight that, again, we looked at in the previous video, which was that if you want to build a spanning tree, so just getting the spanning part right, but maybe not the minimum part, there were sort of two basic strategies we could follow. One is we could start with an empty tree and add in edges that satisfied a certain property, or we could start with the full graph and delete out edges, again satisfying a certain property. So those are the two algorithms that Kruskal is going to use, but let's take a closer look and identify specifically when we can add or delete a particular edge. So in Kruskal's main algorithm, we're going to start off with an empty tree, similar to Prim's, but where Prim's algorithm grows the tree from a single vertex, always adding to the tree that was there before, Kruskal's algorithm is actually going to treat each vertex, if you'd like, as its own isolated tree of size 1. And at each step, it's going to grab two trees out of this set and merge them together according to the edge that joins them. Now, the way we're going to do that, which edge are we going to select? Well, we're going to select edges in order of edge weight, and specifically in ascending order of edge weight, meaning we will start by selecting the minimum weight edges in the whole graph, add those into the tree until we start encountering edges where adding them would create a cycle, and those ones we will skip over in favor of the next one that we can add that will not create a cycle. In this way, we will be adding edges into our minimum spanning tree from the smallest edges up to the greatest edges. And of course, this strategy seems to, this would at least on the surface seem to lead to the minimum total weight. And of course it does. Kruskal's algorithm is indeed a correct algorithm. And let's see if we can actually prove that correct. Now, like in our proof for Prim's algorithm, we're going to rely on the cut property that we proved the lemma for in the previous video. Now, remember what this cut property says. It says that for our graph, if we draw a cut, and the cut is just separating the vertices into one half or the other, and just sort of drawing a line down the middle, any edge that crosses that cut, that joins the two sides, the minimum weight edge we are promised is the part of at least some minimum spanning tree. So if we can argue that the edges that we are adding are part of this minimum spanning tree by using this cut property, then we can argue that Kruskal's algorithm is indeed correct. So let's see how we can apply the cut property here. So to start off, again, we're going to start with an arbitrary input, so an arbitrary weighted undirected connected graph. This is the input to our problem, and this guarantees that we have a general proof. Our proof will apply to any input, not just a specific one we've designed. Now, we are also going to let T be the tree that we want to talk about, the tree returned by our algorithm, Kruskal's algorithm. And we want to argue that this tree is both valid and optimal, meaning valid, meaning that it is a spanning tree. It doesn't contain extra edges, it's not disconnected, things like that. But then optimal meaning that it's the minimum spanning tree. So we can sort of split this in two, the validity part and the optimality part. So I usually start with the validity part, often because it's a little bit easier to argue. Now, as I mentioned, one way we can think of Kruskal's algorithm is as grabbing these two trees, these two disconnected trees, and joining them together by this edge E. Now we know that it's always grabbing two disconnected trees at this step because if it wasn't, it would be creating a cycle, and we will never create a cycle. So as a result, we will never create a cycle. That's built right into the algorithm. So remember, this means that what we return is a tree, and if what we return is a tree that contains all the vertices of the original graph, then it's a spanning tree. And again, that's the criteria of validity that we need to look at. The next criteria we want to look at is our criteria of optimality, and that is, are we guaranteed that this spanning tree is indeed a minimum one? Now, to do that, this is where we're going to invoke our cut property. So we want to say, well, which cut are we considering here? So this one's not going to be a straightforward application as prims. So let's begin here. So at this point, we're going to be saying, say we're considering some step in Kruskal's algorithm where we're adding some edge. Now we could give it a name. I'm not going to give it a name. Instead, I'm going to name the endpoints of that edge. I'll call them U and V. Now at this point, we can say that these vertices, U and V, they might just be not connected to anything at this point in the algorithm, or they may already be connected to other vertices in some subtree. And so what I want to do is give names to these possible subtrees. Again, these subtrees might only contain the single vertex itself, or it might contain more vertices if they have already been connected in an earlier step in the algorithm. So the one thing we are guaranteed, though, is that U and V, as we already argued, that these two must be in two different subtrees of our final tree T, and that's because if they weren't, we would be creating a cycle at this step. So we'll pick one of these two trees out. Actually, it doesn't matter which one. It looks like here I'm going to pick out TV, but we could have picked TU equally. And basically, I just want to consider all the vertices in that subtree, and then all the vertices not in that subtree. That's going to be the cut that we consider. And then what I want to argue is that this edge we are adding is the minimum cost edge that crosses that cut. Now, the way we're going to know that or argue that is the way we've selected this edge is we selected it as the next minimum the next minimum weight edge that we have not yet already added in a previous step, meaning that that any previous edge, any other edge that has a smaller weight has either already been added, so isn't crossing this cut, or would create a cycle. And so we've already skipped over it at a previous step in our algorithm. So since our algorithm is the minimum weight edge in that set, it must be the minimum weight edge that crosses this cut. That guarantees that it must be a part of some minimum spanning tree, so we are correct in adding it to our minimum spanning tree in this step. So this confirms that Kruskal's algorithm then is going to be a correct algorithm. And so let's just take a moment to run through Kruskal's algorithm, a quick example of it. Now, this algorithm actually starts with a pre-sorting of our edges, and I'm not going to sort of sort the edges in any way. I'm just sort of going to visually look here and see, okay, well, we've got an edge here of weight 2. That's the smallest one. I think that's my first one, yeah, so add that one in here. And then I've got another 2 over here. And the criteria for adding them is if they won't create a cycle. So I'll add this one in as well. It won't create a cycle. Now we've got some 3s. Oh, it looks like I got this one first. And then this one over here. Okay, neither of those create a cycle. Some 4s. That 4. This 4. Okay. A 5 doesn't create a cycle. Some 6s. This one next, yeah. 7s. Oh, this 7 creates a cycle, so we don't add that one. But we've got a 7 over here. Now, this 7 added us into this tree. And adding this 7 is also okay, it won't create a cycle. Okay, but this 7 I'm going to skip over. So we're still going to consider it at this step in the algorithm, but because adding it would create a cycle, we'll skip over. Now, there are some clever ways for us to do this, and usually the cleverest way to do that is to have a table that tells us which hash table which tree we are in, using a hash table or a similar type of data structure that makes it easier for us to keep track as we merge these subtrees together which tree we're in. So we could look up our two vertices in that data structure and see they were in the same subtree, and that alone will indicate that adding this would create a cycle. That would eliminate us needing to do a check for cycles, which might take us a linear amount of effort, which might be a waste of time. So we have to be clever if we want to do that efficiently. But continuing our algorithm, we're on to 8s now. Right? It looks like most of our 8s were out of luck. Now this 8 we're going to add. That one's fine. But this one would create a cycle, this one would create a cycle, this one would create a cycle. So all of those will rule out. Now the next up are 9s, and we'll actually quickly check. That's a cycle, that's a cycle, that's a cycle. This one is not a cycle, and in fact we only have 2 disconnected components right now. We have this large tree over here plus this one here. By joining this up, we now have a complete spanning tree, and we can actually do early termination in Kruskal's algorithm by noting how many edges we have. And once we've added the n minus first edge, we know we're done, and we can just signify all the remaining edges as being not used in our spanning tree. Now, which direction we should go in a second we'll show how we can do this from the other direction, deleting, but this early termination saves us some effort. Which way we should go by deleting or adding is not always obvious. Maybe we can, for sparser ones, maybe we want to delete. For denser ones, maybe we want to add in. So that's one maybe rule of thumb we could use, but that's not always going to give us the right answer either. Let's go ahead and take a look at the runtime for our algorithm. It's actually quite a bit simpler for us to analyze than the Prim's algorithm, mainly because the bulk of the effort is carried out by the first step of our algorithm, and that is when we sort the edges. Now, sorting the edges, if we have order E of them, is going to take order E log E using a fast sorting algorithm like a merge sort or quick sort or heap sort. However, we often want to have our runtimes written in terms of E and V, and we'll notice here that the log E, which could be n squared in V in the worst case, would only pop out a constant factor out front. So we actually just simplify the log E to log V. Okay, but what that means is the sorting is not E log E, but it's E log V then, where this is going to become the dominant operation, because then we iterate over the edges, again potentially with early termination, but we iterate over them, and with a clever use of data structures we can check for cycles quite easily without having to run a depth first, for instance. And so this step is actually dominated by the previous step, so the total runtime is the cost of the sorting procedure. Now, Kruskal's other algorithm is going to basically, I think of it as basically the same algorithm, just run in reverse. We start with the full graph, and we're going to delete out edges if they are in a cycle. Okay, and so what that guarantees us, since we're deleting out edges as long as they're in a cycle, we'll delete all the cycles. There's our validity proof right there, and we're guaranteed at the end that what we're left with is still a connected graph, since we won't delete if it is not in a cycle sort. Okay, so for Kruskal's reverse delete here, I just want to again run a quick example of it to show how it works. And to do that, I'm going to, again, we imagine sorting them, but now we're sorting our edges in descending order, and now we're deleting them out as we go if they happen to be in a cycle. So again, we're looking for cycles here. So 13 is in a cycle here, so we'll delete it. We've got some 12s, they're in the cycle, we'll delete them as well. Okay, 11 in a cycle, delete. 10s, both of them are in a cycle. They're sort of in a cycle together, but even after deleting one, it's still in a cycle, so we'll delete it. 9s, okay, let's look at this one first, noticing this one's not in a cycle. Okay, if we delete it, we disconnect this chunk from the rest. That's another way of checking if it's in a cycle. But deleting these two, they're both in cycles, so they can be deleted out. Oops, I think I went one step too quick there. But now we have our 8s. This 8 is not in a cycle, so we'll stay, but these 3 8s are. We'll delete them out. Then our 7, well, these two 7s need to be there, otherwise we'll disconnect. But this 7 does not need to be there. It's in a cycle, so we'll delete it out. And again, we could run some early termination for Kruskal's algorithm if we got to this point. So we might stop here. Again, we check to see how many edges we have in our graph, and if we ever get to n-1, we can just terminate right there. Now, the runtime of the reverse delete algorithm is the same as Kruskal's original algorithm, so I'm not going into too much extra analysis on this algorithm, other than to say that yes, it's also order E log V. Okay. So the last algorithm that I want to take a look at, and I'll just conclude this video with it, is Boruvka's algorithm, which is another sort of interesting variant, not as commonly used as the other two Kruskals or Prims. But I wanted to include it for a little bit of historical context, but also just to show another algorithm that we could use. And there are actually other algorithms out there that we know are correct, but we just, you know, they're maybe a little more complex, so they're just not as worth using. But Boruvka's algorithm, again, was designed by Boruvka in Soviet Russia to do some electrical engineering and wiring up the grid for a city. And the goal was to try and minimize the costs of the grid and therefore minimize the wiring that was used. And so his algorithm was, it's a little bit more complicated in the sense that it takes a little bit more to write down, but it's not really that much trickier in understanding. And you can think of it as using a sort of a queue that's going to be filled with trees. And as he goes, he's going to take those trees and merge them together to finally build a final tree in a very similar way to Kruskal's algorithm, but the order in which he selects his trees is different. It's, in some sense, it's almost like a blend in my mind between a Kruskal's and a Prim's algorithm. So let's sort of see how he does this. So to start out, he's going to go for each of the vertices and treat each one as a tree. And he's just going to stick them in a queue, and for this matter, he can put them in a queue in an arbitrary order. Okay, they're not weighted in any way. Now, while the queue has more than one tree, because when we only have one tree, we're done. Okay, so while it has more than one tree, we're going to take the first one out. Okay, whatever it is, I'll call it Ti at this step. All right. Then we're going to create. I'm not sure if Boruvka was aware of the cut property, but it is here where he's applying the cut property. He is here going to say, now this tree, I'm going to treat it isolated, and I'm now going to find the edge that connects this tree to any of the other trees. Okay, whichever edge it is. And of course, as we're applying the cut property, we want the edge with the minimum weight that crosses this cut. Okay, so we find the one with minimum weight that crosses the cut. It's going to connect us to some other tree. I don't know which one. We'll call it TJ. And we're going to remove TJ from the queue as well, because, so we've removed TI at the first step. We'll remove TJ now. And then we'll merge them together. That will create a new tree. And we'll add the new tree into the queue. And the way Boruvka's algorithm worked, he just stuck it on the end of the, on the end of the queue here. and then pull out the next one. So repeat until we only have one tree left. So in the last step, we have two trees left in the queue. We merge them together, we add one back into the queue, and then we end, because the while loop ends, and then we just return that last tree that's in the queue. That's the one. And just like our previous algorithms, the runtime for our algorithm is going to be order E log V in the more efficient implementations. Okay, so I do want to try to use Boruvka's algorithm here as well. Now, this involves envisioning the queue a little bit, and the queue is a little bit somewhat hard to envision without actually having it on hand. So try and stay with me. I'm going to start by adding all of them in. All of them are trees now, and I've added them into the queue. And I'm going to begin sort of going kind of left to right here. So the first tree we've added, this is the first one I pop out. The minimum cost edge was this one here, so I pop out this tree as well, and I merge them together. Okay. Then I take this tree and put it in the queue, but it ends up at the end of the queue. So next up, I'll take these two, merge them together. Okay. Again, take them, put them at the end of the queue. Now it depends now, what is the next vertex that I get? I think it's going to be this one here. And when I get it, if I do the cut around it, the cut brings me this one here. So we actually grab the same tree again. It was at the end of the queue, we pulled it out, and then we put this whole thing back in at the beginning of the queue again. Again, same thing here. Okay. Now which one do I pick? There was a tie, so I wasn't sure. But again, that pulls out the same one, puts it back at the end of the queue. Continue. I think this is probably the next vertex in my queue. Looking around, we got the 4, so put it at the end of the queue. The new tree is at the end of the queue. Next one here, doing a cut around, we get the 6, so we had pulled this tree out, put it back at the end of the queue. Okay, if you're keeping track of the end of the queue, it's still got all these vertices, and then this one, and then this one, then this one. Okay, next one is this one here, doing the cut. Looks like we get the 6. Add these ones into the back of the queue. Okay. Next one, I'm guessing maybe this node. Okay, and it's the 8, so we'll grab this one out of the queue, put it at the back of the queue. All right. This one here, looks like a 2, so we grab this one, put it back at the end of the queue. And then finally this one here, looks like it's the 5, grab it, put it back at the end of the queue. Now, if you were following the queue, I was doing it in my hand. It's like following cups in a little cup game. But I think they're in the order that they look like here. It's this one, then this one, then this one, then this one. If I got that wrong, well, I guess we'll find out on the slides, or you'll let me know in the comments below. So let's continue. So I think this is the next one I'm going to pull out. Well, it looks like it's the 9 there, so that's going to merge me to this one. That's going to throw this one back into the back. Okay, so the next one I'm going to pull out is this one here, and it looks like the one around that is this 3, so we're going to add that 3 in. Again, that one gets thrown in the back. Well, we're at the final stage now because we only have 2 left, so we find one of them, draw the cut around it. Looks like it's this one here, and it looks like it's the 7 that we get, and we finish the algorithm again with the same spanning tree. Now, I haven't actually verified this, but we've now run 4 different minimum spanning tree algorithms on this this graph, and they've always given us the same minimum spanning tree. So I'm guessing there's only one minimum spanning tree for this particular graph, and we found it every time. So at least the algorithms agree with one another. I guess the last thing I need to do then is prove that Boruvka's algorithm is also correct. I kind of hand waved at it while we were going over the algorithm because the cut property again somewhat straightforwardly appears. Okay, so let's go ahead and see if we can apply it. So we'll start our proof out with an arbitrary weighted undirected connected graph. Again, just generality for our proof, establishing generality by making sure our input is arbitrary. And again, giving us something to talk about, we'll just let T be the tree, the final tree that Boruvka's algorithm returns to us. Now, remember, we have 2 steps here. One is that we want to argue that it is going to return to us a spanning tree. and then that's the validity criteria, and then the optimality criteria is that it's the minimum spanning tree as well. Okay, so again, trying to make that argument, the validity part is just arguing that we don't ever introduce any cycles. Now, the way that we're guaranteeing that is we're always connecting one tree to another one. And again, if we're connecting two trees that are not the same tree, we have no chance of creating a cycle. So this will never create a cycle, so we're guaranteed. And remember, we stop when there's only one tree left in that queue, and that's what we return, the spanning tree. So we're guaranteed that we return a spanning tree. How are we guaranteed that is minimal? Well, again, consider each step of Boruvka's algorithm, where we're going to grab that tree out of the queue and then consider all of the edges that connect that tree to any other tree, meaning all the edges that cross that cut. So that's how we're going to be applying the cut property here. Okay, so again, by our lemma, we know that that edge must be part of some minimum spanning tree. Since every edge that we have is part of some minimum spanning tree, at the end we're guaranteed our final product is also a minimum spanning tree. And that concludes our proof. So in our discussion of minimum spanning trees, we've discovered that there is more than one competing algorithm. For the most part, if we implement these algorithms with efficiency in mind, that they have the same efficiency. So how you select which algorithm you would prefer is a little bit up to you. Although some have maybe benefits if you know a little something about your graph ahead of time. All right, so I do want to finish my discussion of minimum spanning trees here, but I do want to put some little warning signs or little foreshadowing for the next video, where I want to continue talking about graph algorithms, and I do want to talk about Dijkstra's algorithm for the shortest path, and remind you that it follows a very similar pattern to Prim's algorithm in the last video. So thanks for watching this video, and we'll see you in that next video.